Alright, problem 3, it looks like it's a simple function, but it's actually not. This one's one of the harder cases, and the harder, derivative's not the hard part, it's the algebra that's the hard part. And so what I'm going to do with this one is I'm going to show you how you can solve it kind of hand in hand algebraically, but mostly graphically. I'm going to solve this one graphically. So I'm going to do this one a little different than before. So first step though is the same. You find the critical values the same way, or the setup's the same way. Find the critical values, which means find the derivatives. So the derivative of this function is, well, the derivative of x is 1, minus, well, the negative 3 is going to come along. I pull out my power 1/3, take x raised to the negative 2/3. And so my derivative simplifies to 1 minus x raised to the negative 2/3. Remember what that x to the negative 2/3 really means? It's going to be important to understand what it means. That really means the negative means reciprocal, so that x term should really be down in the bottom. So it should be 1 over x raised to the positive 2/3. And if you wanted to take it a step further and rewrite it as the cube root of x squared, you can. Those are the two expressions I'm going to use. So remember what the critical values are. Critical values are when my derivative is 0 or my derivative does not exist. And I actually will have both cases. The 0 case is the hard case. The does not exist is the easier case, but it's only easy if you remember what that negative exponent means. I want to solve for 1 minus x raised to the negative 2/3 equal to 0. Now, some of you, if you're really strong in your algebra skills, you could solve that. Most students struggle with the negative exponent and fractional exponents. And when you solve it, you kind of get stuck. Alright, so because of that, I'm going to solve this graphically. And so I'm going to graph it in a little bit and solve that using the graph. So again, this one's fairly hard. I'm going to graphically solve this. Alright, so I'm going to solve for the zeros, the critical values at the zeros, graphically. If you do solve it by hand, be careful. There are actually 2. A lot of times students can find 1, but they miss the second one when they're solving it algebraically. And if you want to know how to do it algebraically, if you're curious, you can always pop in an office hours and I will go over how to solve that with algebra instead of graphically. But I'm going to do the graphical method because, again, I think most students will struggle algebraically, and so when you struggle, and this is true for any of them. So if you run into a wall algebraically, you can always revert back to, you have a graphing calculator, you're allowed to use it. You can always use your graphing calculator to kind of solve this. Alright, so I'm going to get to the 0 case in a second. Before I do, though, I'm going to talk about the does not exist case. Alright, you can actually look at the does not exist case, and it will show up on the graph, but it's actually easier to kind of understand it before we get to the graph. Which is why it's important to remember what the negative exponent means. Remember, the negative exponent really means reciprocal, so that should be moved down underneath. And so looking at the second expression for the derivative here, now it's easy to see where the where the first derivative does not exist. Right? If I try to plug 0 in to my derivative, I will get division by 0, right? 1 divided by 0 to the 2/3 would give you an error message. And so 0 is a critical value. The check is then, does it exist in my original? Well, my original function, there's no division. It's not a negative. 0 has no negative. Actually, cube root doesn't matter if it's negative. I can plug a 0 in a root. It's fine. And so it checks. It is in my domain. So it is a critical value. Alright, so 0 I've established as a critical value. It's a place where my derivative doesn't exist. There are 2 other critical values. Alright, where this is 0. So, again, if you can solve it algebraically, feel free. I'm going to solve it graphically. I've actually already got it typed into my graphing calculator. I actually have both the original function and the derivative typed in. So, where you'll see my y2, I've already got highlighted. There's my derivative. 1 minus x raised to, in parentheses, the negative 2/3. I'm going to make sure my window is a standard window. I'm going to start with a standard window, and it is. So I'm good to go. So I'm going to hit graph. Alright, and so there's the graph of the first derivative. So there's g prime of x, the derivative function graphed. Now, you'll notice the calculators kind of look at the middle there where x equals 0. It's a little hard to see. And so I'm actually, since everything's sort of tight along my x-axis, I'm going to adjust my window in the y direction to kind of zoom in on what's happening there near the origin. So I'm going to go to my window. I'm going to leave the X's. Those are fine. And what I'm going to do is I'm going to change my Y. I'm going to go maybe -5 to +5 to kind of zoom in. Hit graph and see if it shows me a little better of what's going on. It's a little slow. Alright, so you'll notice here, it looks like the function stops, but it actually doesn't. This is shooting off to -infinity on both sides of 0. Remember, the function didn't exist at 0. There's an asymptote at 0. Doesn't exist. And then you'll notice there are 2 places where it crosses the x-axis. And it is at 1 and -1, but don't always go off of that. Always kind of make sure using the tool on your calculator. So remember how we find zeros. You hit second trace, you pick 2, 0, and then it'll ask you to go to the left of it, the right of it, and guess. So just make sure you go to the left. Move your cursor to the right. And then I'm just going to hit it again instead of guess. And there it'll give me that it is at the 1, 0. You can do the same thing and it'll give you the -1, 0 is also where it hits over here. It's symmetric, you'll see. So I'm going to go back to my notes and graph that now. Alright, so my graph it over here. If I can. There we go. Alright, so I'm actually going to draw my graph over here. So this is the graph of the derivative, right? The derivative. Do it on red, kind of like I had it before. So it crossed twice, right? Crossed at the point x equals 1 and x equals -1, and then at x equals 0 there was asymptotic behavior, right? Came down, crossed. And on this side, came down, crossed. Kind of threw that funky because my 1 was in my way. Let's try that again. Alright, and so there's my derivative function. And so the critical values are x equals 1, x equals -1, because those are the zeros of the derivative, where the derivative equals 0. And at x equals 0, because the derivative did not exist, but 0 is in my original function. Alright, so I do have 3 critical values. Before I go write out my critical values, I'm going to go ahead because I'm going to use the graph to test. So before I go to write my critical points, which I'd have to go back to my original function to write them out, I'm going to go ahead and test for increase and decrease. And I'm actually going to use my graph and the number line. Alright, so I'm going to draw my number line out. So my original function does go from -infinity to +infinity. Give myself a little more room. Mark off all 3 critical moments. So I've got a critical moment at -1. I got a critical moment at 0, and I've got a critical moment at +1. I put my negative on my -1 over here. But one of those critical values is a special case. Alright, so this was a stopping point, so I had a horizontal tangent. This was a stopping point, I have a horizontal. This, however, was a does not exist case in my derivative, and so it's one of my special cases. It's either going to be a corner, sharp change, or a vertical tangent case, which actually I can tell once I do my increase and decrease, and we'll figure out what that is. So this is one of our special cases. Alright, so remember, when we're doing the number line, what we want to test is the derivative positive or negative. And then that tells me if my function's increasing, moving up, decreasing, moving out. And instead of picking test points, I'm actually going to use the graph. Alright, remember, this is the graph of the derivative. Alright, the derivative is positive when it's above the x-axis. Right, here's my x-axis. And it's negative when it's below the x-axis. And so if I look at my graph here, this piece and this piece that I've highlighted in yellow there are where it's positive, right? Because it's above the x-axis. Then this piece and this piece are where it's negative because it's below the x-axis. And so my derivative is positive from negative infinity to the first critical value, negative 1. And it's positive again from 1 to infinity. It's negative from negative 1 to 0 and from 0 to 1. At 0, it's nothing. It doesn't exist. It is neither positive or negative. It's not increasing or decreasing. All right, something special is happening there. All right, so now writing that in my table without having, so I don't have to do test points. I just have to write the information down now in my table. So it was positive at the tails, negative in between my negative 1, 0, 0, and 1. All right, so this tells me what's going on. So when my derivative was positive, it means my original function's increasing, it's moving up. Then it stopped at my first critical value. Switch directions and is now moving down. It does not exist at 0. It's not a stopping point. It's a does not exist special case. On the other side, though, what happens is it continues to... So that tells me what's going on. It's not a sharp change. It's not a corner, right? It doesn't change direction. And so that tells me, and the graph will reflect this, that this does not exist case is a vertical tangent case. Right, and my graph should reflect that. Alright, then I still have to finish off my picture. From 1 to infinity, the slopes were positive, so it increased. Alright, so now increase, decrease, decrease, increase. Stopped. Didn't exist means doesn't increase, doesn't decrease. It's a special moment. Stopped, increased. Alright, now writing that all out, we'll start with the critical moments. Alright, so at the critical moments, you'll see it's moving up and moving down, so this means this is a max. This is just a critical, neither a max or a min. It's a special case where I've got a vertical tangent. And then at 1, it was moving down, switched to moving up, and so this would be a minimum. So at the critical points, negative 1, g of negative 1, which I'll find out what that point is in a second. This is a relative max. Right? Because at negative 1, it went up and it maxed. At positive 1, g of positive 1, which again I'll find the point in a second, that was a minimum. So at that stopping point, it was a relative min. At the special point, at 0, g of 0, it is just a critical. It's still important, but it's not an extrema, not a max or a min. And it should reflect, it's a vertical tangent. It's that special case where I've got it's that special S shape where I get a vertical tangent out. And my graph will reflect that. So now I find my value. So negative 1, 1, 0. So I go back to my original function. My original function was x minus 3 times x to the 1/3 power. That's the original. That'll give me my y values. And so when I plug negative 1 in, I get negative 1 minus 3 times negative 1. So that's going to come out positive 2. Positive 1 minus 3. So that's going to come out negative 2. And when I plug 0 in, I get 0 out. Alright, so my maximum is at 2. My minimum is at negative 2. My special point is at the origin 0, 0. Alright, now write where it increases and where it decreases. Alright, so my original function, g of x, increased at the ends over the interval negative infinity to my first critical point, negative 1, and from 1 to infinity. Right? That's what my table said. Negative infinity to negative 1, it increased, moved up. From 1 to positive infinity, it moved up. G of x decreased over the intervals negative 1 to 0, 0, 1. Now, if you had written negative 1 to 1, I'd probably accept it, but technically at 0, something weird's happening. It's perfectly straight up and down. So, straight up and down, well, if I'm moving perfectly straight up and perfectly straight down, am I perfectly increasing and perfectly decreasing at the same time? What am I doing? And so that's why it's sort of an unknown. We write it, it's a vertical tangent, and it's neither increasing nor decreasing because the slope doesn't exist at that moment. And so we don't really include 0, but if you had, I probably wouldn't marked it wrong. So there's my answers. Now the check step. All right, so to check, we're going to graph. So this is a different graph. I'm going to graph the original, g of x. All right, that's the original function, which is what we're talking about. All right, I use the derivative to find my critical moments. Now I'm going to go back to the original and write them down. So again, going back to the original function, which I have in my calculator already. Alright, so kind of checking everything. So the graph step is the check. So I'm going to go into my graphing calculator. I'm done with my derivative. So I'm going to go down here and I'm going to clear out my derivative. I don't need it anymore. Since I already have it typed in, I'm just going to highlight that to make it show up. You can retype it and just make sure you're careful. Make sure you put parentheses around that 1/3 power. So you get x minus 3x to the 1/3. I'm going to leave my window because I can actually see that it's going to show up just fine. So the window that I had in there, remember I changed it to 5 and -5. I'm going to leave it. I'm going to go to graph. And so when this function, I'm going to go to graph, maybe it'll take me right. There we go. And here's my original function. It should reflect everything that I've stated. It should have a maximum where it has a maximum, a minimum where it has a minimum, a vertical tangent where I said it had a vertical tangent, increased and decreased accordingly, and it does. You'll look here at 0, 0. It looks like there's a break. There's not. If you hit second trace value, type in 0, it says it does exist at 0 and the value is 0. There's my vertical tangent spot. It's a critical value and it's perfectly vertical there. And you can see that the graph reflects that. My maximum was at -1, so I hit my value key, type in -1. There's my maximum at 2, right? -1, 2. My minimum is at 1, so type in 1, and there's my minimum is at -2. And so I did find all my correct values. It increased where I said it increased, and decreased where I said it decreased. Alright, so now drawing that out clearly on the graph, and labeling all the important points. Alright, so 0, 0 was an important point. 1 and -1 were important points. So 1, 2, 1, -2. So there's my -1, not -1, +1, -2. This is my -1, +2. My graph comes up, and then again approaches perfectly vertical at 0, 0, and comes down, and then shoots up again. And so at 0, 0, there is a vertical tangent. Actually, the vertical tangent is the y-axis. Alright, so it's perfectly straight. So at 0, 0, we can't say it's increasing or decreasing because it's perfectly moving up and perfectly moving down at that moment, right? My slope is undefined. So at x equals 0, slope is undefined or does not exist. However, these, it's 0, right? My vertical tangents are there. This is a relative min. This is a relative max. This is a critical, but it's not a max or a min. It's my vertical tangent case. VT, vertical tangent. It did move up from -infinity to my first critical value of -1. It is moving up. From -1 to 0, it's moving down. Now, at 0, technically, it's perfectly straight up and down, so I can't say it's moving down because it's also moving up. Alright, so we say after 0, though, it's still moving down again. Alright, so from 0 to 1, and then from 1 to infinity, it's moving up again. And so it reflects what I stated. It increased where I said it was increasing, positive slopes where I said it had positive slopes, negative slopes where I said it had negative slopes, a vertical tangent where I guessed it had a vertical tangent. And so this is this function. So this one is a toughie. Whenever you have a vertical tangent case, it's always one of the harder cases. And so this is, again, one of the tougher examples, but you should, again, hopefully understand it a little better after seeing this example done out. Alright, well, I'm going to stop there. I'll pick up the logarithm case in the next video.